systems of equations with nonlinear equations. So I want to remind you, in a previous video I discussed solving systems of linear equations, and I reviewed a few methods. Some common methods included graphing, substitution, elimination by addition, or use of matrices. Now in this particular video, matrices will not be the most helpful, neither will elimination by addition. So for nonlinear equations, you only want to use these two methods in circumstances where the exact same type of expressions. Graphing and substitution, sometimes independently and sometimes together, will be the most common type. So again, only use these two methods if your equation contains common expressions. Graphing and substitution will frequently be the most useful method for these types of systems. I'm about to solve a few. The following 5 sets of equations will be the systems that we look at. Now, it is important to keep in mind there are situations where a solution could not or will not exist given by your constraints. And so in those situations, just keep in mind that I would like for you to explain why no solution exists. So to begin, I'll look at number 1. You'll notice you have a line as well as a cubic function. I'm going to discuss this using substitution. So because I have a line, I noticed that it would be very easy to isolate y here. So what we'll do is isolate y so that we get an expression y equals 2 minus 3x. Now that's completely equivalent to that first line. What we'll do then is substitute that into the second equation. By combining like terms and getting everything in ordered, so it's in standard form on the left, I look and I notice that that's a cubic function, and I can factor out an x. That leaves me with x times a quantity x squared minus 3 is equal to 0. Because you have a product equal to 0, that gives me 2 equations. X could be 0, and there will also be solutions, 2 solutions, from when this term, x squared minus 3 is equal to 0. That gives me that x could be positive or negative square root of 3. This equation that fell from substitution has 3 solutions. By substituting those back in to my red equation here where I isolated y, so because I have these 3 solutions for x, plugging that into this red equation gives me 3 solutions for y, and I find the 3 solutions to this system are points, they're ordered pairs. So when x is 0, y must be 2. If x is positive square root of 3, then y would be 2 minus 3 times the square root of 3. So you'll notice if it's plus for x, it's the subtraction sign for the y solution. And if x is equal to negative square root of 3, when you plug in negative square root of 3, this becomes a positive, and so the y value would be 2 plus 3 square root of 3. Like lines, what we're doing here is we're solving for all of the points where these 2 graphs would intersect, the graphs of those 2 equations would intersect. So for this particular system, we have 3 solutions. In the next example, you'll notice again I have a line, but the second equation is a circle. So it's a circle with radius 5. I again will talk about using substitution here. By isolating y, I can substitute that into the second equation. By multiplying this out, so expanding this red term, I get 16 minus 8x plus x squared. By putting everything on the same side, I notice I have a quadratic here, so putting everything on the same side, I would try to factor, but I do notice that isn't going to factor very quickly. So if it's a quadratic, always put everything on the same side, try to factor. If that doesn't get you anywhere, you can try the quadratic formula. So here, negative b would give me a positive 8 plus or minus the square root of b squared minus 4ac. When I simplify that, the square root of 136, so 136 I was able to factor out of 4 times 34. A square root of 4 gave me a 2, 2 over 4 gave me a 1/2, and 8 over 4 is where this 2 came from. Pause the video if that doesn't make sense, but if you're familiar with the quadratic formula, you just use the quadratic formula and I simplified my radicals. This gave me 2 solutions for x. That's telling me I may have 2 intersection points. So when x is the positive value or when x is that negative value. To find the y values, I again can now substitute this in for my x, and I get two solutions. So the x value here corresponding to the positive sign would correspond to the y value with the negative. And again, the x value with the 2 minus would correspond with the 2 plus. Keep in mind that this was a line and a circle. We might want to look at the graph of that in just a second, but this work that I'm indicating here is how to solve that algebraically. For the third problem, I want to look at a cubic polynomial as well as a quadratic. Now, because I have both of these given to me in the form y equals, I could set those equal to each other. Put everything on the same side. Perhaps factor if possible. I notice that I can continue factoring this. I had a greatest common factor of x. I am now left with a quadratic that factors into x minus 3, x minus 1. This cubic equation is now factored on the left into 3 prime linear factors. This tells me that I have 3 solutions possible for x. That would be at x equals 0, 3, and at 1. Since I have those 3 values for x, I'm able to plug those back in for either to get y. Now you can use either equation. I want to stress that. I always get it's common for me to hear the question, well, where do I plug that back in? Since these x values should be solutions to both of those equations, you should be able to plug those back anywhere. Use whatever is most convenient to you. It is pretty obvious if you plug 0 in for x, you'll have y equals 1. If you plug x equals 1 in, you'll have a little bit of arithmetic and you'll notice you'll get negative 1. And if you plug 3 in, so I encourage you possibly use the second equation. It might be easier. Things cancel and you'll just have 3, 1. This tells us that these pair of equations, a cubic equation and a quadratic equation, have 3 intersection points. So the solution set contains 3 ordered pairs for this system. Now if you're more visual, then I want to show you the graph of that. We have graphed cubics and quadratics pretty frequently in college algebra. When I look at the graphs of these, so you'll notice my cubic must be this red graph. The gray function is the graph of the quadratic, and you'll notice they intersect in exactly 3 points, which we just found algebraically. Now, of course, using a graph, that would also make this quite easy. In Desmos, those become a piece of cake. I do want to stress that you practice these algebraically as well. This is a common technique that you could use in other science and math classes and will be necessary in higher math classes. Looking back at another one that one of the previous problems, here I have a line and a cubic. Again, we already solved this. I know that it was somewhat of a messy solution set. We had 3 solutions, and you'll notice they are indicated here. What I'm wanting to point out right here is this would have been the algebraic solution. If you were needing to have that algebraic solution, perhaps for a math class that would not let you use a calculator, then a graph is helpful to help you understand how many intersections are, but this graph, unless you have a particular type of calculator, wouldn't give you those exact solutions. Sometimes sneaky teachers, such as myself, will take away your calculators for quizzes or tests because we want you to understand this algebra. A graph is helpful to understand those number of solutions, but taking away your calculator forces you to understand the algebraic techniques as well as the graphical understanding. In this homework, I want you to use those ideas together. I want to see some of these algebraic solutions because I want to know that you understand how to solve quadratics, solve cubics, and solve these equations we've worked with for quite a while. However, I do encourage you to type those numbers in and check them with a graph to make sure that you do understand how to get those values. Another one we looked at, this would have been quite difficult. I realized the algebra on this was a little bit more intensive. So I do want to point out we looked at a line and a circle, and we did get 2 solutions. If you want to type these numbers into a calculator, you'll notice they are the 2 indicated points on that graph. So again, a graph is very helpful. It makes it quite easy to find your solutions instantly. if you are trying to understand the algebra, you can use those two ideas together to ensure that you're using the correct methods. Here I have given you an exponential system. So I have two exponential equations. Again, we have y equals, so I could set these equal to each other, put everything on the same side, and you'll actually notice on the left-hand side you have an equation that is quadratic in terms of e to the x. I could try to factor this. This particular equation does not factor nicely. And so again, if it's a quadratic, I'm going to use a quadratic formula. It is not x equals, since this was in terms of e to the x, but e to the x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Simplifying this expression on the left, I simply add 9 and 8 to get the square root of 17. Since that's prime, there's really no more we could do. I now have two equations. E to the x is equal to this right-hand side with the positive, or e to the x is equal to this right-hand side with the negative. Something I want to point out, 3 minus the square root of 17. Now since the square root of 17 is greater than the square root of 16, which is 4, I know that I'll get 3 minus something that's here, this numerator. If I use that minus, it would give me a negative number. E to the x cannot be less than 0. However, so that would not result in any solution set. The only solution I will get is from looking at the positive term, 3 plus, and by getting x by itself, solving for x, I can take natural log of both sides so that I get x is equal to natural log of that right-hand side. Now I realize this is a messy number. What I would do to get y is I could plug this number into either of these equations. Immediately I'm thinking the second equation would be easiest. If I plug natural log of something into e and natural log are inverse functions, they cancel, and I simply get 3 times this expression, 3 plus the square root of 17 over 2. So my solution here would only be the single ordered pair, my x value, natural log of that expression, and 3 times the value inside the argument of natural log here, so inside these parentheses, 3 times that would be my y value. I do want to look at a graph, so I'll throw the work back up here. We've got one ordered pair, and if you throw that in a calculator, at least do me a favor and pause the video. Make sure that when you type this into a calculator, you at least know how to get those values. That's important. So throw those into a calculator and see if you can get these decimals for that. The two graphs that I have here, so if we were in class, I'd also spend some time making sure that you remember your translations. If I have e to the 2x minus 2, that's an exponential graph translated down 2. So you'll notice that definitely is going to be this black graph. You'll notice it's growing faster than the red graph because it's e to the 2x, not just e to the x, and we've translated it down 2 values here. Another trait, 3e to the x, so 3e to the x, you'll notice it has a bit of a stretch, that 3e to the x. It certainly wouldn't grow as fast as e to the 2x, but 3e to the x is a vertical stretch there. 3 is what's doing that. So this would be a graph and the algebraic solution for that system. The last problem that I had in that opener was a system of equations with a sine function. Now, I know we haven't worked with sine as much in college algebra, but as we get closer to that, this graph, this system really didn't have much work to it, and you could use a calculator for this if you'd like. So sine of x, if I substitute the two equations inside of each other, you'll notice since y is equal to x, I could just plug that in so that I get sine of x is equal to x. Sine, you have seen the graph. I know that you might not understand where all of the values come from yet, but you have seen the graph, and then that only intersects the line y equals x at this single point 0, 0. It is actually, we'll talk about tangent lines later if we talk about derivatives, but they only intersect at the point 0, 0. So this system has one solution. It's the ordered pair 0, 0. I'm going to pause this video and let you all look at those problems. I encourage you rewind, fast forward when it's necessary in these videos. In the next video, I'll talk about solving systems of inequalities. I'll discuss both linear and nonlinear equations.